Before we will go directly into reduction formulas, we need to do some special cases of trigonometric integrals. So also I promised you to show you how to find the integral of secant x dx. It's really very tricky. But you know, if you experiment a lot, probably you will get to this point that you can guess that you have to multiply by something and divide by the same thing, and this thing happened to be secant x plus tangent x. If you notice, then what is written on top, which is secant x times secant x tangent x dx, is exactly the derivative of secant x plus tangent x. So du is going to be secant x plus tangent x. And again, the du is secant x. If you derive, you get secant x tangent x. And the derivative of tangent x is secant to the power of 2 of x. So you get exactly this. And this is ln of u in absolute value plus c, which is ln of absolute value of secant x plus tangent x plus c. Let's do one example with the finite integrals here. Okay, so it is this. And secant of pi over 4 is radical 2, and tangent of pi over 4 is 1. We get that this is ln of radical 2 plus 1. So before we will do the reduction formula, we still need to work out this integral. And by the way, used in this integral is the previous integral of secant of x. So sometimes trigonometric integrals can be done only by parts. This is a really good example. Recall integration by parts. I need to split the secant cubed x dx to two parts. One is going to be the u and the other will be the dv. It's pretty screaming at me that secant to the power of 2x dx is going to be the dv, because we know that the derivative of tangent x is secant to the power of 2 of x. So I'm going to take the dv to be secant to the power of 2x dx, and then obviously I stack with u to be secant of x. But I can take u as I want because it's always easy to differentiate. So if u is secant of x, du is secant x tangent x dx. And this one, v is tangent x. That was the reason for that. We'll use the regular setup for the by parts, and we get that. So now I have still to integrate secant x tangent to the power of 2x dx. But now I have an idea. Why not use Pythagorean identities here? Tangent to the power of 2 is secant to the power of 2x minus 1. I'm substituting secant to the power of 2x minus 1 instead of the tangent to the power of 2, and see what I get. I get here two integrals. The first one is the original one, and then an integral of secant x dx. We just did this one, isn't it? Yes. So I know what is this guy. So now I can use algebra, really. So I get that the integral that I like is secant x tangent x minus the integral that I need plus that. So let's use algebra here. So I get that 2 times the integral that I want equals secant x tangent x plus ln of secant x plus tangent x in absolute value plus c. So I can finish this up by concluding that this is secant x tangent x plus ln of secant x plus tangent x in absolute value over 2 plus c. But observe even more. If you look at what I got here, Okay, I got a little reduction in a way. I started with secants cubed x and I reduced this to the need to actually evaluate secants to the power of 1 x dx. So maybe there is a reduction for the integral of secants to the power of n x dx. Recall the previous example. We started with secants to the power of 3 of x. Integration by part, etc. And I end up with that. So if I wouldn't really finish everything, I suspect that there is a reduction of 2 in the exponent each step. This technique, when doable to any exponent, it's called reduction. So in the following example, we will find the reduction formula for the integral of secant kx dx, and we will show how to use it. Example: we are going to find a reduction formula for the integral of secant kx dx. We will start. In this time, we are going to do integration by parts. For that, we have to split secants to the power of kx to a product of two functions. I'm going to split the k exponent to k minus 2 and to 2. Because I do not know how to integrate secants to the power of k minus 2x to any k which is greater than 2, this is going to be the u, and d of u is going to be k minus 2 times secants k minus 3x times, chain rule, secants x tangent x dx. I can combine the secants x to the power of k minus 3 with secant x, and I get the du is k minus 2 secants to the power of k minus 2x times tangent x dx. The dv is secants to the power of 2x dx. I have to do it because I get very easily that v is tangent x. So let's use integration by part, and we are going to get that. Now I see that I have an integral of secants to the power of k minus 2x times tangent to the power of 2x dx. I'm going to use the trick that we used before. I'm going to replace tangent to the power of 2x by secants to the power of 2x minus 1. Now I get this. We are going now to distribute the secants k minus 2x with secants to the power of 2x minus 1. And we get that. Observe that we get two kinds of integrals now. We get the integral of secants to the power of 2k x dx, and also we get secants to the power of k minus 2x. The first one is what we are looking for. The second one is already a reduction, because instead of having an integral of secants to the power of 2k x dx, we have an integral of secants to the power of k minus 2x dx. In this step, we can use algebra. If you look at the beginning and the end here, you can see that we have that the integral of secants to the power of 2k x dx, this is what I'm looking for, equals to secants to the power of 2k minus 2x tangent x minus k minus 2 integral of what I want plus k minus 2 integral of secants k minus 2x dx, which is reduction already in the exponent of the secants. The next step is going to work out this algebra to get what is 1 time integral of secants to the power of 2k x dx. So as you can see, both of those integrals are integrals of secants to the power of k x dx. And the leftover, I really don't care, it's just a leftover. And what's nice about this leftover thing, that it's including an integral of a lesser degree than k. Now the degree of the secant x is k minus 2. So now let's combine everything and be really careful with the algebra. Okay, we have 1 time my integral that I like to find, and then we have minus k minus 2, so we have to add k minus 2 of this integral both sides. So we get k minus 2 plus 1 that we had before. So we get k minus 1 of the integral that we are looking for to be equal all the rest. So now the only thing that left to do is divide everything by k minus 1. And I get that. It looked terrible, but it was really easy to get. And actually, if you noticed, I use exactly the same technique as I used with secants cubed x. This is a reduction. Now I want to use that to see and to check that I didn't have any mistake when I use this to find the integral of secants cubed of x. So let's take k equals 3 and see what we get. So k is 3, so 1 over k minus 1 is 1 over 3 minus 1. And then we have secants of 3 minus 2. And then we have, instead of the k3, so we get 3 minus 2. And the exponent of the second one is 3 minus 2, which is just 1. So we get that. And if you recall, the integral of the secant x dx is ln of absolute value of secant x plus tangent x. Now it's more complicated. Now we want to use the reduction formula to evaluate secants to the power of 5x dx. This is going to be pretty messy with algebra, so we have to be very careful. So first I start with k equals 5. You really want to simplify every step of the way. And we get that. Now I need to reduce this one. Don't forget all those parentheses. So I have to replace this by that. And I get this. Now the only thing is to substitute for the secant x dx, okay, and we get this one. If you look, this is like something in something in something in something. This is really what we get, unless we will simplify further, which we are not going to do. We are going now to find another reduction formula, this time for the integral of tangent to the power of 2kx dx, where k is greater than 2, and obviously an integer. All those reduction formulas are only good for integers. Then we are going to use it to evaluate the integral of tangent to the power of 4x dx. We will start again as we did with the secants to the power of 2kx by breaking down the exponents to k minus 2 and 2. We are almost going to go back and do the same trick. I'm going now to rewrite tangent to the power of 2x as secants to the power of 2x minus 1. Now we will distribute tangent to the power of k minus 2x. Let's observe now what we have. The first part is an easy integration using U substitution, because the derivative of tangent x is secant to the power of 2x. The second one is a reduction because it's an integral of tangent to the power of k minus 2x dx. Let's evaluate this one using U substitution. U is tangent x and du is secant to the power of 2x dx. We get that, which is just u to the k minus 1 over k minus 1, and in this case tangent to the power of k minus 1x over k minus 1. The second one we just copy. You can observe the reduction. And here is our reduction formula. The integral of tangent to the power of 2kx equals tangent to the power of k minus 1x over k minus 1 minus the integral of tangent k minus 2x dx. K equals 4, so I'm just substituting 4 for k, and I get that. Simplify all those numbers. I don't care about the tangent cube x over 3. And I have the integral of tangent to the power of 2x dx. But this is really easy if you use the following trick again. This is what? Well, I can just use again the reduction if I want. And I get that. The integral of dx is just x, and I get that.